Very nice to see all of you here once again on the last day of our 6-day workshop on electric vehicles 2.0 emerging innovations and trends in the Indian context. In this workshop, we have reached the last day, that is 6th day. We are starting our session by none other than Dr. Chandrasekhar Nadamurti. Sir is the Senior Specialist for Electronics EV Practice, L&T Technology Services, Bangalore. Now I request, I think yesterday we have introduced Dr. Chandrasekhar Nadamurti. I request Dr. Chandrasekhar once again, and I welcome him on behalf of the Department of Electrical Engineering. Welcome you, sir. Now over to Dr. Chandrasekhar.
Okay, very good morning to you all. Am I audible?
Yes.
So, yeah. Yesterday we already had our discussion, right? So, can you please ask for Evans, we can ask Evans. Okay. Okay, as I discussed with Madam and Sir, they said that some of you are not there in yesterday's our discussion. Okay, so just I thought that we can have a brief overview what we discussed in yesterday's. Then we continue with the remaining part. Okay. So initially we started with the role of power electronics. Now where we'll find power electronics in our day-to-day lives, and also where we find power electronics in electric vehicles. So just I'll explain high level what we discussed in yesterday's discussion or lecture. Then later we'll start this portion. Okay. So anyone got chance to visit this COP28? Yesterday we discussed it, right? Now it is ongoing. It started on November 30 and it will be up to December 20. Okay, now it is in UAE, Dubai. It's going on. But as I already discussed, it is a what do you call? It is a conference of parties. Uh, it is mainly conducted by United Nations. It's mainly focused on the climate change action worldwide. So from every country, the government representatives or their PMs, they will go to this conference, and on behalf of their government, they will give what are the actions they have done from the past year on climate change, and what are their plans, and what is their target for zero emissions. So as we discussed yesterday, it is from our government, it is our government has promised to the world that we will do the net zero emissions by 2070. Okay, so our government has promised to the world that we'll work towards zero carbon emissions by 2070. So it is as government has promised, they promised on behalf of the country, right? On behalf of me and you. So this is our responsibility to contribute for this. Okay. So we already discussed this. If you get chance, you can visit this present COP28 Conference of Parties, United Nations Climate Change Conference. This is what we discussed. This already we know. Transportation is the main one of the polluting industry, and so the solution is we have to move from fuel based to coal based to the electric vehicles. That's what we discussed. Right. This slide is about this one interesting slide we discussed. It is of the life cycle of the carbon emissions. If you take one IC engine, IC car, in the whole life, how much emissions it will contribute to the. So we understood that it is, if you are taking one car, gas powered or a Toyota, so in a life it will contribute or produce 68 tons of carbon emissions. If you are taking EV, it will be 15 tons, right? So there, it is just to show the importance of moving the transport to the EV side or electric vehicle, electrifying our vehicles. So these all are we discussed everywhere. So from starting to ending till 2029, 2023, so everywhere the EV market has grown, right? Yeah, this is one beautiful slide we discussed yesterday. So this slide covers almost all parts of our globe and our life as well as industries, right? We discussed yesterday already. So you can see on this side, these are the equipment our operators, appliances will use every day, maybe at our home or offices or industry, right? So even for the generation, we will use solar, wind and energy storage, and electric vehicles. Everywhere we will see that maybe we don't know that there is a power electronics, but we understood that this is power electronics is everywhere, but we are not able to see that. It is unseen, unheard, but it is working from the background. Okay, that's what we discussed. I don't want to spend much time. You can see here everywhere power electronics. Correct? So everywhere. You can see the appliances, solar, energy, fuel cell, electric vehicle, energy storage, batteries, solar, wind. But whatever we will take, everywhere we will see, we will follow the power electronics. So this is what I have written. Power electronics everywhere. discussed 70% is processed by power electronics, in future it will be. So we concluded that from this slide, our understanding is if we have better power electronics, our life will be better and we will have the and savings also, because losses will be less, and power electronics definition we already know. So here I highlighted this part, not only conversion from one part to or one to another, but important is efficient conversion. That's what power electronics will do. This is about again the growth of power electronics. Previously we discussed about previous slides, it is EV. Now it is power electronics. You can see the growth in 2026. Even you will take converters, inverters, onboard chargers, or in the fields of automotive, railways or marine and airborne vehicles. Everywhere we can see that there is a lot of growth in the power electronics, and we already discussed where power electronics in electric vehicles, right? This slide also we discussed yesterday, right? So our grid, it is AC, but my battery which is sitting in my car, it is DC. So if you want to charge that battery, we have to convert the AC into DC, right? For that we need something that is your power electronics. So that's what we discussed already, right? This is our onboard connection or grid connection. So we have to convert the AC into DC, and as we already discussed, when we are dealing with the grid, we have to maintain the power factor, right? Otherwise we will be penalized from the government. So we have to maintain the power factor. So this is one section where it has to convert AC to DC, as well as at the same time it has to maintain the maximum power factor of 0.95, right, above 95 to 97. And we have to follow the strict norms, right, as per the government of India and the international standards, ISO standards and IEC standards, right? And there are restrictions for the what we call harmonics, right? IEEE 519, you might have heard that IEEE 519 2000. No, you have to follow the international standards, IEEE standards for harmonics, even current harmonics as well as for the voltage harmonics. Okay, less than 5%, less than 3% we have to maintain. It is also based on the number of harmonics. If it is up to 50 harmonics, 50th harmonic, then you have to maintain that less than 5%. Okay. So there are a lot of, I mean to say that just, so here it is very, very important when you are connecting to the grid. So whatever you have designed here, it should not disturb the grid. It has to cooperate with the grid. Okay. So for that we have to follow the EV standards as well as for the ISO and IEEE and IEC standards. Okay. Yeah, this is just we already discussed. We have to convert AC to DC and again power factor and DC to DC. This is your battery, bidirectional converter. This already we discussed, right? These all are same, simple representation. So in EV, usually we will be having two batteries. Okay, this is just one more. This is your high voltage battery. It mostly depends on the, it is for the inverter and your motor. So where we need, as discussed yesterday, so these are DC bus in or we'll call it as a DC link in literature. So general standard voltages are 800 volts, 400 volts and 150, 120 also there for 3-wheelers. So next it is will be 1200 or 1500 volts. Okay. So this is one battery. Actually this DC link means it is a battery. Next you will be having one more battery of 12 volts. So this is for your lighting, heating and auxiliary loads, whatever we will use in the car, small, right? So or infotainment, we will have display, right? in the car, in new cars and all, you will find infotainment. So for that and all, we need 12 volt supply. So this is already discussed, just to, and ultimately it is a car, so it is driven by, your wheels should be driven by the motor, right? For motor, it should be driven by power electronics, right? You have motor here, AC motor, so but your, this is DC and this is AC, so you have to convert the DC into AC, right? Again here, this is also DC, this is also DC, but this DC at 400 volts, but this is DC at 1200 volts. So again you have to do DC. And important, we already discussed, when we have one voltage is at high level, one is at very low, so we cannot connect directly through power electronics converters or devices. We should have to provide the isolation, right? So that's why whenever you see this, so you will have the boxes and in between you will have the your high frequency transformer, right? This is not our 50 Hz transformer, but it's high frequency transformer. So we will operate at some 20 kHz or more than 20 kHz, so that your size of your transformer will be reduced, because it is onboard charger. It's sitting in your car, right? If I am keeping our 50 Hz transformer of 2 kV or something, it will come like this. Usually our charger will be like this. A whole onboard charger, it is this much of size, right? If I am keeping the 50 Hz transformer of 2 kVA, then it will occupy this space. Then what about other parts, right? That is the beauty of engineering. We do electrical engineering, power electronics, right? So you will play with the high frequency. So when you are playing with high frequency, then the size of magnetics, right, it will be reduced. But always there is a limitation on increasing the frequency. As we discussed yesterday, there is most of the components or companies, their products are delayed to the market because of EMI/MC failures. Because they will design and they will operate at high frequencies, they will not take care of this EMI/MC. So when you are operating at high frequencies, you want to high frequency in the sense, what is high frequency? Frequency means it is one time period, right? On and off, right? So during that, if I will have 50 Hz, then my devices will be slowly turn on and turn off. If I will increase 20 Hz, 20 kHz and 100 kHz, my device will turn on, turn off, turn on, turn off, right? So when it is turning and turn off means it will be voltage and current change, dV by dt and dA by dt, right? So it should not affect the other components, right? Even it is working in my converter, it should not disturb the other converter. That's what we discussed yesterday, right? EMI, it is a problem. Electromagnetic interference. You are creating the problem. This is compatibility. Compatibility means though you are creating the problem, I am not able to affect. I will not get affected because I have that compatibility or stamina, or we can say in our COVID time we discussed, right? We will have good what do you call immunity. So I have immunity. So though you disturb or create a EMI, so I will not have any problem. So one thing in industry, when you wanted to go with any product, first you should not create problem, right? And next one, even others will create the problem, you should sustain. So you have to create or design your converter or your system or a product in such a way that it should not create the problem, at the same time it should not affected by the others, right? Even within the car or within the board, component to component, we are not talking about system level. If you are taking two ICs, this is one IC, this is one IC, right? So because of this, it should not be affected, and because of this, it should not be affected. Even it creates a problem, it should have that compatibility. Understood? This is very, very important. This is very good research nowadays. In industry also, industry needs a lot of support from the academia on this EMI/MC. Even I told yesterday, recently I have personally submitted 4 to 6 proposals on EMIs. Some of the companies, their product is ready, they wanted to deliver or market, but everything is ready, but they failed in the EMI system. Okay, so yeah. So this is, we already discussed, right? You have grid, this is AC, but my battery is DC. So you have to convert AC to DC. At the same time, we have to maintain our power factor. What is 99? 99.5, 99.7 you have to maintain. So this is overall your EV. So here you can play with the source. Suppose if you want to do the project, you can keep this everything and you change here it solar PV, right? So it will be DC. Or you can play with wind, this is AC. The wind output is AC, right? The solar output is DC. Next you can play with fuel cell, this is also DC. Super capacitors, this is also DC. So you can do multiple, and inside also you can play with the modulation techniques, means control. You can propose new control technique, right? So always industry expects you should not include new hardware if you have solution without introducing the new components. Or means I have charger, I have some problem. If you can give me the solution without changing my charger, anything, or without introducing any new component, then that will be best. That's what they want. First they'll ask that solution. Can you do something with software? Means control. First proposal will be, if you can propose something with control, write some new proposal, let's say okay, I have EMI MC issue. So if I give some solution like no need to change your hardware, I'll make it with software. I'll do some coding and inverter switching and all I'll change so that your EMI MC will be reduced. Then understood. These are the challenges in the industry we are facing, or all the industries, right? As you all are mostly PG and PhD and faculty, so these are very useful for you because this is what we do in industry. Yeah, this already discussed. I think it's not required, but important is just you will have the 2 batteries. This is called HV battery. This is our LV battery. This HV battery is mainly for traction. Traction in the sense to drive your wheels. So, but remaining this 12 volts battery is for remaining whatever you have 12 volts, lighting, fans, or cooling, or AC, something, right? Auxiliary loads. This is one important. This is already discussed. There are a lot of, mostly we use onboard chargers, outboard chargers, and wireless. Now we are working on wireless also. In our company also we are preparing one, building one wireless charger. Right. These already maybe previous colleagues, many of them are discussed. I don't know to touch this. So this also we discussed yesterday, right? So you have AC/DC converter like this. This part we are talking. So you can use multiple converters. We can use based on the diodes, or we can use with the switches. But ultimately we have to maintain this power factor. But usually with the diodes we cannot maintain. That's why we'll go for the full converters with the switches instead of diodes. Okay. And next one, as we discussed this converters, if there is not much difference between this HV side and LV side, we can go with non-isolated converters. Isolation means this is my input and this is my output voltage. So isolation means the ground. Either you have the common ground or different ground, right? So when we have 2 different voltages or high voltages, we have to maintain isolation between the first side and next side, or primary and secondary, or HV side and LV side. Okay, so that's what you can see here. When you have the low voltage, or suppose I can say here 48 volts is there, and I have 12 volts. So 48 by 12 is only 4, right? Only 4 times. So no need of isolation, right? Isolation in the sense, it's not only for the equipment, it is for the human, right? So if we have difference like this, it is 800 volt system and this 12 volts. So 800 by 12, what is the ratio? I can take 10 and 8, it is 80 times, means it becomes 70, right? So if you have 70 difference, there is a huge difference in the current also, right? Always current voltage differences. So you have to introduce transformer isolation. Okay, so this already we discussed, right? We need, these are the main research now. Many of PhDs also they working. This is my PhD topic. Initially we started with this dual active bridge. So dual active bridge in sense, yesterday we discussed it, right? This is just 2 inverters separated by a transformer. So in 2015-14 this is a hot topic. Now you will find the reference material also on this. It is very good topic for PG and PhD, or faculty also they can contribute more, because now industry is looking for this DAB. There are challenges in the DAB, dual active bridge, because we have to achieve the soft switching, right? No soft switching, right? Because okay, we'll discuss later, because yesterday we already discussed. So when we want bidirectional power flow, so bidirectional means we should not use switches, diodes, right? Diode is just, it is a basic knowledge, it is unidirectional device. So whenever you want bidirectional, you have to change, you should change the diode with the switch, because the switch can operate in, it can work in both sides, right? Your diode switch will work when it is turned, and otherwise your diode will be conducting, right? Power can flow, current can flow in from this side to this side, or this side to this side, right? So that's why when you don't want, like suppose here, this 12 volts DC is there, right? So mostly this battery will charge from high voltage battery, but it cannot charge 800 volts battery, right? Correct? It is 800 volts big battery, like I can say this much battery. My 12 volts battery is this. Always what you have to do, you have to take from the big one, right? But small one it cannot support. That is the basic. So in that case, what you have to do? Do we need to include the switches in the secondary? Not required, right? Because it is a cost. Whenever introducing some new device, it is a cost. And diodes are cheap. Whereas you wanted to use the switches, we will not use the silicon switches. Now we are using all our SiC based. Silicon carbide, all MOSFETs, silicon carbide MOSFETs. Only in inverters, we will use the IGBTs, right? Because these motors are very high power, right? For high power, we have to go with IGBTs, right? So it is a basic question, you already know that. So mostly in DC-DC converters, we will use SiC based MOSFETs. For inverters, we will use, because inverters, will not use more frequency. It will be around, in our simulations and all, we use 100 kilohertz and all. But always, suppose you have inverter. Okay, so I have here DC. We have inverter. The operation of inverter, it purely depends on your load or application. Suppose my application is traction or motors, then this is motor, right? So you have to design your inverter, or all the parameters selection will be based on the motor. Because what you have to do, suppose in general, in inverter you will have your fundamental frequency as well as switching frequency. But when you are playing with motors, it will come another frequency, it is electrical frequency, right? So we know that speed formula, right? 120 F by P. This is your electrical frequency. So based on the number of poles and the speed, you have to calculate this Fe. This Fe will be your fundamental frequency for your inverter. Understood? So in general, we can play with the frequency selection, but like our simulations, whatever we'll do in our labs and all, so I'll keep the R node, RL node, and I can increase the frequency 10 kHz, 20 kHz, 30 kHz. But in industry or in the real time, it's based on your application, whether it is connected to grid or it is connected to the motor, right? So if it is motors, if it is a grid, we can play with the frequency. Same inverters, no? We can operate at 100 kHz. There is a reasons, because when you are playing with motors or grid, important is the harmonics. It should be, you have to follow standards. 2009, 919 and all. So always you have to maintain that less than 5%, less than 3%, right? So we have to follow the standards, international standards. Okay, so this is one important. Okay, so I mean to say that this DC-DC converter, it can be non-isolated or it can be isolated based on your requirement. So that's why, so maybe I might have good knowledge and design experience with this bidirectional converter. But if the application is only the 24 volts to 12 volts, right? In that case, I cannot go for this, because in industry, I have to purchase everything, right? I have to give order. So for that, for my management or my head, I have to give the justification. Because suppose some customer, it is only 40 to 24 to 12 volts DC-DC converter. So if he is giving only some 50 lakhs project. So 50 lakhs project, if you wanted to use this all SAC devices, whatever recently in the past 2 years back we purchased an SAC device, they are 8,000. One switch, it is 8,000. One SAC device, it is 8,000. During the COVID, we made this onboard charger, it is 8,000 rupees. And during this hardware, how many MOSFETs we blown, we don't know. Simulation, it is okay, right? You just give the pulse and get the output. But in hardware, so you don't know. For L&T, it is not matter, because it is millions and trillions. But thing is, from our side, we have to understand. So simulation is different from the hardware, right? Yeah, we will move. You understood, right? Just I am trying to share the knowledge, so you will get the interest. So tomorrow you can work on, or you can share the same knowledge with your friends or colleagues. Yeah, this is already we discussed, right? This is a basic converter, is a buck converter, right? Your switch, diode, and the your inductor, right? So it will be only unidirectional, we discussed already. So if you want bidirectional, you need two converters, one and buck and boost. So instead of that, I can replace my diode with the switch, so it can operate in bidirectional. These also we discussed yesterday, I already told, right? Both are 3 kVA transformers, but the frequency matters. It is 50 Hz and this is 20 kHz. Size, this is what we are discussing here, right? So these are isolated transformers. These also we discussed. As we discussed in the previous slides, so this is nothing but this one inverter, right? This one inverter. And this is your transformer. So if you know inverter operation, then easily you can implement this DC-DC converter, right? And we already discussed that operation also yesterday, right? These are the different isolated converters we will find in the literature. Even ATAL Mohan textbook and Rashid textbook, you know, power trunks, Rashid and Red Mohan, they are, right, and Ericsson, they are famous power trunks textbooks, right. So you can see isolated converters. For small power, we can go with this flyback, forward and half bridge push pull. But we'll go for the high power, that whatever I discussed in the previous slides. We can use that understanding. This is what I'm talking. If we understand the inverter operation, same inverter operation, then your AC will be converted, DC will be converted to AC, and AC again based on your turns ratio, it will be step down or step up. Mostly it will be step down, and again your AC to this is your rectifier, diode rectifier, AC to DC, right? But here I have battery. Okay, so when you are converting this DC into DC, ultimately what you are doing, we are charging this battery. When you are charging the battery, again the norms will come into the picture. So you have to follow delta V and delta C. This is called ripple content, right? During your basic rectifiers and all you will study, right? Ripple factor and all, right? So one important factor is when you are charging your battery, you have to maintain the ripple current and ripple voltages, mainly for ripple current. Otherwise, so if you have the more ripple current, then you are feeding that ripple current to your battery, then battery has to accept, right? Charging, discharging, the ripple, because of the ripple, again the heat will be generated and your battery life will be, suppose if it is guaranteed for 20 years, it may go in 5 years. So important is, so that's why we'll use here another inductor and capacitor as a filter. Whatever you are converting AC to DC, it will have a lot of ripple, right? So it's supposed to be expected is like this, right? But you will be having a lot of ripple sitting on that AC component. So we have to remove this AC component with the help of the filters. Filters means we have to introduce L and C. So that's what, this is a famous topology for chargers. If you are using without this filter, this is called full bridge. If you are adding inductor here, that is called PSFP, phase shifted full bridge. That is the main topology we will use in the chargers. Okay, this is one topology. Another, we will add inductor and that is phase shifted. Next one, DAP. These three will be in your most of the electric vehicle chargers. Wherever you go, it will play with this. Otherwise, they will introduce some resonance here, RC, resonance circuits. So you write in your basics, right? So what is the reason for going to resonance circuits? Why will introduce the resonance in our circuits?
Make it resistive.
To make it resistive. So what is happening? The losses will be minimized, right? Suppose if I may turn on and turn off like this, right? In between you will have the losses. So if you can make that once my device is turned off, then if my voltage is 0, then my device is on. So here you don't have losses, correct? So but if it is like this, before my voltage coming to 0, my device is already started. So you will have this triangle, right? This is your losses. So what you have to do? You have to first make your voltage 0, then you start your device. So there will not be any overlap. So your losses will be 0, right? This is on, this is off. One is on, one is off. There should not be any, what do you call, interaction, right? This is called soft switching. This is another research area. Now the research world is working. Soft switching, with the help of soft switching, there are two types of soft switching, you know that, right? ZVS and ZCS. Zero voltage switching, zero current switching. So this is another research area you can work. So when you turn on, your losses should be 0. When you turn off, your losses should be 0. So finally, the efficiency in the sense, loss should be minimized, correct? Once the losses are minimized, then only I'll get maximum efficiency. So that's why now research world, they are working on, here they will introduce L and C. Then it will be your resonant error. Okay? Then they will say that the efficiency is more than 98%. Otherwise, it will be 95 to 96. For the 2%, it's very, very important for industry. For us, it will be your numbers. But for them, it is a money. Right? Because if your efficiency is 98%, to bring that to 100%, somewhere they have to increase the filters, they have to add extra components, and to make it efficient. Right? So, always in industry, it is your efficiency is equal to your money. Everything is in the money. Your efforts. Yeah, okay. Yeah, this is one example I try to explain in high level, and this already material I shared with sir. Okay, sir will share. It is available in the literature. It's available in the Google. Just you type 6.6 kilowatt high power density bidirectional EV charger, you will get some 60 pages report. Okay, so from here I try to explain what you already discussed, right? Okay, so this is what we will do in industry. So when customer comes and he'll say that he will not give any high level, he will not give any details. He'll say that my input is this, my output is this is my power. So he will not give any other parameters. Then we have to do lot of with our engineering expertise from their high level information to specifications we have to convert. Specification in the sense final parameters, design parameters. Customer has given only 3 parameters, you have to convert that into 10 to 20 parameters. With your expertise, with your experience and continuous discussion with your customer, and they will come up with some solutions, we have to come up with some solutions. Finally, you have to convince them with that, okay, whatever we are giving, that is the best solution. Then they will be happy and they will release the funds and we will get the business, right? So for that we have to do a lot of research and you have to choose the best converter for their application. For every application we cannot put the same converter, right? So as we discussed. And again, you have to develop the control. Okay, you have to select the proper control, and control is not easy. This I am talking about simulation, not in the hardware. So for simulation also what we will do in industry, we will not use the same MATLAB ideal devices. We will use the devices of the manufacturers. Suppose if I am using for my application in hardware, if I want to use what we call 3.3 kV IGBT 600 amperes, okay, same device I have to mimic in the simulation. There are softwares which can mimic your real device. One software is this Flexing software is there, PLECS, Flex. Okay, there and manufacturers will provide this data, or XML files also. Freely it is available. You can import those XML files, and then so this is converter you can see here, this example. So usually if I want to implement with the MATLAB Simulink, okay, so what I will do, I will put some DC and ideal switches and this, but you can see here, right? So this is the device, this device is from here. It is not your ideal device, but it is our real device. When you are importing an XML file, it will be from manufacturer. So whatever they used, no, internal parameters, everything for the switch. What is on voltage, off voltage, what is threshold voltage, what is the EON and EO. When you switch on, you will get EON losses, right? If you see the data sheet, you will understand these parameters. When you will see the data sheet, I forgot to include the data sheet. Otherwise, I would have explained in detail about the data sheet. So if you have one data sheet for one switch, the data sheet will be 30 to 40 pages. But for us, just we will see only what is the voltage and current. It is 3.3 kilovolts voltage and 600 amperes. But for that, you will have on parameters, off parameters, diode parameters, MOSFET parameters, again on state, off state, and important thermal parameters. Right? So this is what you can see here, no? What is this? This block is the heat sink. Whatever we use in the real world, here we can use that heat sink also. We have to design the heat sink. That's what you can see here, right? So this is what yesterday we were discussing. If I have the MOSFET, okay, or IGBT, from IGBT to MOSFET, again you have one backside you have some aluminum or copper, right? If you take one IGBT or MOSFET. So that IGBT to that also you will have some resistance. After that you have heat sink. From that cover to heat sink also you have, case to heat sink also you have resistance. Again that heat sink to, you will use some cooling arrangement, right? Sometimes you will use the water as a coolant. Sometimes you will use a methanol, no? Glycol, 50%, 50%. So it is also having some resistance. So if you are taking the thermal resistance, you can see here, junction to case, from device to the case, backside you have one resistance, case to heat sink also you have resistance, and heat sink to the fluid or water or ambient, whatever you are using, it will have resistance. So we will design that. That's what in real it's happened, right? If you keep on device, so how it will get the cooling? Directly it will not come to your MOSFET or IGBT, right? So you will have the water or coolant. From coolant to heat sink, correct? Heat sink to your device case, right? So that's what we are mimicking here. You understood? This is a beauty. It's what we will do in engineering, right? These are real simulations. So here, whatever the numbers I get here, they should match with the hardware. This is what an industry will do. If I do the MATLAB simulation, no, there will be 50 to 60% or 70, 80% error, because I am not using the real devices, correct? But here we will match the numbers. First we will simulate through the softwares and we will get some idea. Then we will do the hardware and we have to match and we have to show the customer. So these are the simulations, this is the hardware, these are the losses I got in simulation, these are the losses I got in the hardware. So you see the matching. Then they love. Understood? So this is, it's interesting. And that too, I explained one more thing right here. Generally, if you open any data sheet, they will give the maximum temperature, so 150 or 175. But when you are designing, we should take the margin. Suppose my device is maximum junction temperature is 175, but I will take only 140 or 150 because I have to give the margin. Because in real time, I don't know what will happen sometimes. Though I designed through this stringent, I followed stringent rules and the real devices I use, still I will take some safety factor. Because in the real world, we don't do, right? Something might happen and it may generate more heat. So my device may got damaged. If the device means it is not a device, right? If one MOSFET is gone means whole converter is gone. One converter is gone means your total charger is gone. It is not only money, maybe we spent some 5 to 10 lakhs, but 1 year effort, 1 year engineering effort, right? And 1 year engineers, suppose 10 people are worked, 10 months salary for them. This is what industry or management will see. For our side, it will be only one device gone. But for management, they will calculate this. Okay, for this project we use 1 year. 1 year, 10 engineers. One engineer, one associate engineer, one senior engineer, one tech lead, one specialist, and finally me, senior specialist. So these many engineers we use, this much salary I have given, but finally it is blown. You understood? So this is what, everywhere we are responsible, we are accountable. If I am working with this charger, whatever I tested, I told, I have multiple, some 10 to 8 people under me. So at last, I have to face the management. If this gone, if this charger has gone, I have to face the management, I have to give the proper reason, I have to convince them that okay, this is what happened, it's not a general mistake, but it is technical, something has happened, something, and we have to convince them. And based on your performance, your salary increment will be there. It's in industry, it is 6 months you will have the review on your performance. Its review is not only your manager, it is from all the people, those who worked with you and their customer and customer feedback and your manager and your subordinates. All feedback will be there. Based on that, your salary